Okay, so good afternoon. Welcome to this afternoon session, where I will be first presenting an overview of the Dislib library. Okay, so this is a bit the outline of this afternoon presentation. We will first go through an overview of what is the Dislib, and then on the DS array, which is its main data structure, and a summary of the supported methods and some results that we have obtained with this library. Then I will present a bit the machine learning basics, very basic. Okay, so probably some of you know much more than what I will present. And a bit what is the typical workflow in Dislib through a sample code. And I will show a bit the internals, okay, so how this is developed with PyComs, okay. And then I will also show a bit the website, the Dislib website, so you can see the documentation, how it's organized, okay. So what is the Dislib? The Dislib is a machine learning library, which turns out to be parallelized with PyComs, okay. So we started to work with some examples of machine learning, like the k-means and other clustering examples and other examples. And then thanks to a project we had with Fujitsu, one of our colleagues decided to try to build a machine learning library, okay, collecting these examples and offering a unified interface, inspiring scikit-learn, okay, which is based on the fit predict methods typically. We will show the example. But the characteristic is that it's based on its own data structure, the DS array, which is a distributed data structure. By this distributed, I mean that the data is not on a single node, but is using multiple nodes of the computing infrastructure. For example, in a cluster, if we have multiple nodes, okay, like in Mare Nostrum, when we will do the hands-on, we have multiple nodes of the Mare Nostrum being used under control of comms. The data, this DS array will be distributed on the memory of these multiple nodes. Okay? It offers multiple methods, between them for data acquisition and other methods for clustering, classification, etc. And all of them, the parallelism is hidden to the user. Okay, sorry, they are asking me about the camera. I will add the camera. 1 second, I forgot the camera. Oh, where is my mouse? My mouse is here. Okay, can you see me now? Okay, sorry. But you can see the screen, the slides, eh? Okay, that's not very well. Anyhow, I'm with a mask, so you cannot only see part of my face. Okay, so it offers multiple methods, as I was saying, no? For loading the data, initiating the data structure, and then different methods for clustering, for classification, decomposition, etc. And the interesting thing here is that the PyComs parallelism is hidden to the end user because it is inside the machine learning library. Okay? So the goal of this session is a bit to disseminate a bit that we have this machine learning library and that you can use it as end users, but also to illustrate how you can parallelize a set of methods, in this case, a machine learning library, using PyComs. No? So we try to show the two things. Okay, so the basics of how we parallelize this library in this case is the data is assumed to be two-dimensional. No? In the rows, we have the samples of the different data that we want to classify or clusterize or whatever. And the columns are the features, okay? And we organize this two-dimensional matrix in blocks. Okay, so one parameter of the different, at least for the initialization of data, is the size of the block, which we can discuss later about this. So given this block size, we decompose the DS array into these blocks, no? And internally, then each of these blocks is a NumPy array, okay, for which then we can use all the NumPy functionalities that are available inside Dislib. Okay? And also, if NumPy is also linked, for example, with optimized libraries like MKL or other libraries that are internally also parallelized with threads or with OpenMP, you can get extra parallelism, okay, at the core level, for example. Okay, so then internally these blocks are organized as list of lists, okay, and the Dislib manage this data structure, so you don't need to worry about it. Okay, and the important thing is that you can operate on these objects as regular Python objects, although it may be not stored in your local memory, so you will instantiate operations as they were in local memory, but in fact the data can be in remote nodes, okay? And what is more, maybe it's not all the time in memory of the different nodes because it can be serialized into files, enabling to support very large data sets, okay? And this is handled by Python, okay? There are different methods for initialization of the data, no? Like loading from different types of files that we will see, or generating as random arrays, etc. And you can have like indexing, slicing, as you do with regular NumPy arrays, okay? And you can also apply some operators. And the nice thing is that this is extensible, okay? If any of you wants to work with this library and wants to extend this set of operators, this can be done, okay? All the code is open source, so you can add operations or you can suggest improvements and we can develop them also, okay? And in this case, with the DS array, what we represent in the blocks and the NumPy arrays are the samples, okay? The labels are also represented with independent DS arrays. So you need to store samples and labels on different DS arrays. And I was saying also that the data not necessarily is always all in memory, okay? So with this we can support what is also called out of core operations, okay? Enabling very large support for very large data sets, okay? The restriction is that this block, the size of the block, fits in memory, or if you have multiple tasks operating at a time, that the addition of all the blocks at the same time fits in the memory of the node, no? So all the nodes and all the blocks that you want to operate at the same moment. This is a summary of the supported methods, okay? Some methods to initialize data from files or from random data, or some utilities to scale, apply functions to a DS array. Then we have operations for matrix decomposition, like PCA or the QR that has been recently added. Methods for clustering, we will in the examples how to use k-means or the scan, for example. There is one of these methods which is not in scikit-learn, which is the Tauro, or also known as Gromos. This is a specific clustering algorithm for molecular dynamic data. Okay, so we add it, even it's not that common because we have users from life science that are using it. Okay? As here, maybe know this algorithm. For classification, we have the CSVM that we also see in the examples, and the random forest classifier, the alternating list squares for recommendation, which is the algorithm from Netflix. For the regression, we have some algorithms for regressions and the random forest regressor also. This also has been recently added. KNN, and then these other methods are not the traditional estimators. These are methods for selection of parameters. We will see also an example in the tutorial, in the hands-on, which are methods that are used combined with the other methods to find out which are the best parameters in order to find the best configuration to train the model, for example. Okay? With regard to how well or how bad performs the Dislib library, here you have some results. In this case, are for the k-means clustering. We have other data, but I didn't want it to be too exhaustive. What we are trying to show here, for example, with this data set with 1 billion samples of 50 features, we see in blue the performance of the Dislib, and in orange the task. TaskML is another library based on a similar idea of tasks also. We see that we perform faster. No, here is time, so less is better. But the other important thing is that if we look into other cases, well, here it appears also, but for example, with this larger data set, TaskML, we are not showing numbers because we were not able to run with these configurations with TaskML. Or similar here also, we are also trying to compare with MLlib, which is the machine learning library from Spark. And we were only able to run these 2 points, no? With the other configurations that we see in the chart, we were not able to run due to problems with memory. Okay. Okay, so then if we go into a bit of some very basic ideas about machine learning, probably you know that there is 2 different types of machine learning algorithms: unsupervised, where we try to find patterns, okay, from data that is not labeled. For example, in clustering, we will see this with k-means, for example, or methods that operate on supervised, what are called supervised methods, which work with labeled data. Okay, so we already have the samples and a label for each of the points. Okay, and we can then, for example, do classification, and based on this classification, then predict the label for other samples. No? Or in the other case, what we can do is when we have a point, try to predict in which group, for example, if we do clustering, in which group you will put a given point, for example. This is a sample for clustering. We will see a similar thing in the demo. Okay, we see here, for us is very clear, not that there are 3 groups of points. Okay, but if you are not able to represent this graphically, this is not clear. No, so with what the clustering is doing here is to say, okay, these 3 groups are very different, and in this case, this is the red dot is the centroid, no, the center for these points, assuming a geometric center. Okay, so this is what the algorithm does, finds that there are 3 groups. No, so this is useful when you have a large data set and say, well, can I somehow cluster this data and see if there are different behaviors depending on the parameters. In this case, we can represent, because it's 2 dimensions. With 3 dimensions, we can also represent this. But if you have much more dimensions, how we will represent this? No? If you have much more features than 2. Another case is the classification. In this case, we already have the data. You have the points, but also you have the label. No, you already know a characteristic in this case of these points, that ones are labeled as red points and others are labeled as blue points. No? And what we try to say is, well, can we somehow identify some characteristic of these blue points and of these red points? So if I have a new point here, I can say, okay, no, this will be classified as red, or this will be classified as blue. No? In this case, it's quite difficult, no? And we have outliers, no? We have here red points that fall into the blue area, no? And will be mispredicted, no? If you try to predict here again, you will say that this point is blue, no? It will be a case that the prediction will be wrong, no? For example. Okay, then what is the typical way of working with in this case, the same idea of scikit-learn, no, with estimators. An estimator, we can say that is anything that can learn from data, no? Even it's labeled or unlabeled. And it will use basically two methods. The feed method, that given a data set will learn, no? And will generate a model. And then the predict. The predict is when you already have a model that has been fitted or trained, okay? And then you use this model to predict for new for new samples. Okay. In some cases, what we do is if we have data that is synthetic, we split the input data set into the training part of the set, for example, 75%, and then a part of the data set is just for test, for prediction of the test data. Okay, you will see examples of this also. And the typical workflow in Python can be like this. No? First, you read from a file, in this case, train CSV, have some input data, and you load into X. Okay. And then you have another file with the test data, and you load this into X, and therefore test. This will be very similar in scikit-learn. What is the difference here is that X and Xtext are not NumPy arrays or other data sets that are more traditional from Python. These are DS arrays, okay? And we are using this function from Dislib, and we are giving it the block size. So the block size is the first parameter is the number of rows, and the second is the number of columns. Okay, so it will decompose this input data into blocks of this size and store it in memory of multiple nodes as a DS array, and the same for the test input file. Okay? This is for the input data. Then, for example, we can instantiate an estimator. In this case, is a k-means estimator that requires to define the number of clusters that you want to generate. In this case, we are using 10. Okay, and then you can call the fit methods, for example, with the train data, and then you can use the test data to predict. Okay, and in scikit-learn, this will be very similar, and the difference here is that the different methods for loading, for fitting and predicting internally are parallelized with Python. So some internals about how this is implemented. For the DS array, first we have that it's implemented as an object with some main parameters. The block size, okay, so that is the shape of the regular block. And then the blocks are organized as lists of NumPy arrays. So inside the block, it's contiguous in memory, but between blocks, they are not contiguous. That's why we can distribute it in memory in different nodes of different memory spaces of different nodes. No? And we can also have sparse data. So one of the parameters of the DS array, if it's the data is sparse or not. Okay. Then how we parallelize this? No? For example, we have here this call underneath in the box in the bottom that creates a random array, a DS array of 100 by 100 and of block size of 25 by 25. Okay. What is internally doing? So in this case, we have 100 by 100 divided with 25 is 4. So it will create 4 by 4 blocks of consecutive memory. And for each of these blocks, we'll call this task that creates a random block. Okay, in this case, you see it creates a single block of the shape that you are passing. In this case, will be the shape will be 25 and 25, and return. No, and well, it's doing more things. No, the creation of the array, but we'll add this block into a list. We'll have one list for each of the rows or columns, and I don't know by heart now. And in the other direction, you will have the columns. Okay. Or another operation, for example, is that you can compute the mean of the different blocks that you have in a DS array. No? So we have this generic function, for example, apply along axis, and an axis can be 0 or 1, depending if you apply this function for rows or for columns. So here you can pass different operators, okay, to compute. In this case, is computing the mean of the different elements in a column. Okay. Internally, this apply along axis is also implemented as a task. No? So if we have multiple of these tasks running at a time that don't have data dependencies, is where we obtain the parallelism. I think I have annotated something and I don't know how to erase it. No, here, or is the screen that is already? No, I think it's the screen somebody painted. physically in the splitting. Okay, so let's go now to a sample code. In this case is the cascade support vector machines. Okay. In this case is a parallel version of the support vector machines that is a very well-known algorithm for classification. Okay. So in this case, we are doing a parallel approach where we divide the input data into blocks, okay, and call internally to the to a function that does the SVM of that block. Okay, so we do it for all the blocks, and then we do a merge operation that applies also the SVM locally to the merging of two blocks and so on. Okay, so and it builds a kind of inverted tree of tasks. We will see that as graph how it looks, and this is done in an iterative process. Okay, in each iteration, we apply this this idea again. Okay, in such a way that we have multiple iterations where in each of them we have some parallelism at the beginning, which is reduced at the end of the iteration, but again we open parallelism again in the next iteration. So in this case, the external loop is here. No, we do this do iteration until we reach the convergence. Okay. Inside this do iteration is this function, this box underneath, and you see here with the initial data x and y we partition into sets of blocks, no pairs of blocks, and we call this train operation. Okay. Later also these results are appended in a list, and the same idea of splitting into blocks. And again, I don't know why it cannot be seen the whole function, but here it's calling again to train underneath in the last row. Sorry. So it's applying this for each of the two blocks that are the result of the previous iterations, okay, the previous trains. And internally, this train here is leveraging the support vector machine basic operation that we have in scikit-learn. Okay, so as we see here is the basic operation for the scikit-learn support vector machine. Okay, so for each of the pairs that we are decomposing the input data, between others, we call to the fit of the scikit-learn basic operation, and this happens in other algorithms. We see the similar idea that we use the BS array as a way of decomposing the problem in multiple blocks. Okay, and then for each of the blocks we apply with a basic operation of scikit-learn. Okay. Here, the rest of the operation is combining part of the result. Okay, in order to return the data in such a way that we can go through these other iterations here that combines the different blocks. Okay. And this is the sample user code. No? For the user code, as you see, we don't have any PyComs operation here. We import the dislib, and we load the data, in this case, in a sparse format. Okay, this SVM-like file is a sparse data file in blocks of 5,000 by 22. In some cases, the blocks are quite big. Okay, you know, don't think that the blocks are a small thing. We instantiate the cascade SVM. We invoke the feed, and well, then the return will be the trained model that we could use for predict, for example. Okay. And this is how it looks. In this case, two iterations of the CSVM. Okay. The first iteration, each of these iterations correspond to the whole do iteration function here. Okay. In the first iteration, we can see some blue and white tasks at the beginning. These are the initialization tasks. Okay, so these are not the SVM itself. The red ones are the ones that are the SVM invocations. So these are the tasks that we before were looking at here. No, the train task. Okay, are these red ones here. And we see the data dependencies. No, we see that between them, every two of them, we do a new operation here. Yeah? Well, if this is not uneven, it's odd. So we have here another one between them. And this will be another iteration. In this case, we run only 2 iterations because if not, the task graph is very big. And you can also generate a trace file, as was commented in the first session. No? Daniela was telling you that we have this possible generation of trace files. In this case, it's a visualization of the task, no? With different colors. We have the same colors as with the task graph, okay? And each row represents a thread, okay? So we have here multiple threads running at the same time. Okay, at the beginning we have the initialization task, and then this kind of pinky tasks are the train tasks. No, that we saw that there was this inverted tree, and we can see here, no, how the parallelism is executed. At the beginning we have many tasks executed at a time, and later, due to this structure of the task graph, we see less parallelism. No, okay. Here there is the end of the iteration, and then we start again another iteration. Okay. In this case, we have quite a lot of load imbalance here, no, because of this task graph configuration, which we cannot avoid right now, okay, because it's the algorithm structure. Okay. In other algorithms, this will not happen. In other algorithms, we have ways of avoiding this, no, through some techniques like trying to overlap part of these iterations or things like this. Okay, so with this is the overview. Before I move to the browser, I will just show the last slide, so I don't have to commute between the slides and the browser. You can have well, this is generic to comms. No, I think you have these links from the other presentations also, but particularly for the Dislib, you have also the GitHub available as a public open source, where you can check out the code if you want. Okay, and in this case, for the hands-on, we will be using the same PyComms CLI, and the notebooks that we will use were already in the set of nodes that you were downloading before. Okay. Okay, so now I would like to show you the website of Dislib, so you can see where you can find the information. So the URL is Dislib. Is dislib.bsc.es. Okay, so right now this is redirected and goes to a read the doc, but the original website is dislib.bsc.es. If I type it. Okay, so basically what you have is you have some quick start, which is with a previous version of the. So here it's not with the PyComms player. It's with a specific tool for the Dislib. But if you have the PyComms CLI, you can use the Python CLI, and you don't need to install this. Okay, but it's the same idea that we did with the PyComms CLI. Okay. You can also look at the user guide. Okay, and you have information on how to run the Dislib, some more information about the DS array. This, for example, no, about how to decide which is the right block size, no, because the problem is that if you do very small block sizes, in principle you will have more parallelism, but it can have more overhead also. And if you do very big block sizes, on one side you have less parallelism, but also you need to be careful that the size of the block is not that big, that then it's larger than the memory of the node. Okay, so you need to be careful. So it's a bit a trade-off. This is something that maybe it will need some rework, not thinking of how we can help the users to decide this. Okay? Okay, then you have some, for other examples, you have also documentation here, etc. And then you have, that we will be using during the hands-on, the API reference. Okay, so here you can go to the different methods. For example, I will show now an example with clustering. So you can go to clustering and you can go to k-means, for example, and it has the methods that are available and examples of use. Okay. Be aware that these examples of use are not with not Jupyter notebooks. So if you want to use Jupyter notebooks, you will have to rewrite them a bit with boxes. Okay. But or if you run it in Mare Nostrum or in other system running without notebooks, you can use this code directly. Okay, any questions so far? No, you can see my chat. I thought the chat was not shared. You can see here, not probably not them. No, or I don't know how it works. Okay, if there are no questions, I will go to the practical part.
No questions in the chat.
Yeah. Okay, thank you. I think, okay, I will stop. Hold on. Sorry. I first stop and I will start from scratch. Vale. So I will start the system the same way we were doing before. Okay, so first with the PyComps init. And so if you are starting from, let's put on the notebook side here, basically in the same directory where you have the codes that you download. Okay? So you can start the PyComps environment. Okay? And then you start the monitor, PyComps monitor start. Okay. And so then, or either you take this URL here and go to a browser and you open the monitor and the username is root. Okay. And right now I don't have any application because I don't have not run anything. Then you go back to the command line and we start the monitor. The Jupyter commands PyComps Jupyter. Okay. And now you have the URL. This is this one. Open. Okay, this could it be that this is not working for me? I usually use localhost directly. I usually use localhost. So if for any of you doesn't work, for me what it works is this one for the notebooks. Localhost instead of 127. Okay. And here I'll go to the syntax directory. And I will start with notebook 9, Dislib demo. Okay. This one you can just listen to me if you want, or you can try to play it at the same time as I do it. Okay. I don't know. It's the 9. It's in syntax and then no 9 dot. see tutorial apps. Inside tutorial apps in Python. Tutorial apps, Python, notebooks. See? Okay. Okay, so if everybody wants to run with me, I will be explaining and running at the same time. Sometimes it's difficult to follow if I'm explaining file location. Okay, from tutorial apps. So that, can you see my screen? So from those that you downloaded before, you go to the Python directory and then to notebooks directory, and inside notebooks into syntax. Thank you, Christian. Okay, so we will start with the same beginning. Okay, we start initiating the PyCom runtime. Okay, and well, the first thing is a bit different, but it's not surprising. No, we import the Dislib as DS, so the same way you will import another Python library. Okay, and here the first boxes are a bit a demo of how you will initialize some data. No. For here, I'm creating a random DS array of 500 by 500 in block sizes, with a block size of 100 by 100. Okay. How many blocks are we going to have? We have 5 by 5 rows of blocks. Okay. Okay. If I print the shape, it tells us that it's 500 by 500 of blocks of 100 by 100. In this case, the data is not sparse. Okay. In the next box, what I try to see this data of one of the blocks. No, if you want to look at the data, you can use this data structure, the underscore blocks in the DS array is where you can find the blocks. Okay, the different blocks. So this would be the data for block 0, 0, row 0, column 0. But you see that it's saying that it's a future object. Okay, this is because, as I told you, we initialize the data with tasks, and then this data is not in the local machine. This is like kind of a reference to this block that is somewhere. So if you want to really access the data, what you can use is the collect primitive. Okay. This will wait for the different data and collect it into the main node. So be aware that this is a very large array. You can run out of memory. So we will not always do this. Right? We will do it in some cases if it's necessary. Now that I've done the collect, if you try to go back to the previous block, it's not anymore a future object. Now it has the values there. Okay? Because we have collected the data in main memory. Okay? Well, don't collect again. Don't do the collect again. We are now going into this other example, into the box below. In this case, is directly initializing the data with some data that I saved. No, it's 2 rows by 3 columns matrix, small matrix, and I organize it in blocks of 1 row by 3 columns. This is a small case. Okay. You can also initialize with the CSR, which is a sparse matrix format. Okay. If you indicate that the data is sparse, in this case, if we are passing a sparse array, it will detect directly that the DS array is sparse. Okay. But you can do also similar with if you are reading from in this case, if we try to print it, it will say that in this case is a sparse data. Okay. You can also load sparse data, for example, from the SVM Lite format, which is a format which stores data sparsely. So you can load from a file, in this case, that you have locally. Okay. This runs correctly for you. The files, you have the files available. If you're trying to load the data, here is one of the. Please go at SVM file, the one below. This one. Oh, did you type here? No, try to. I think you didn't. Okay. Okay. So if anybody has problems with the files, I think that they were correctly stored in this files directory. But if anybody has problems, let me know. Okay, and then you can also do, for example, slices or slicing of data. No? In this case, for example, we are creating a random array of 50 by 50 rows and columns in blocks of 10 by 10. Okay? So you can get here just a single row. If you type x parenthesis 4, this is the fourth row, okay, or the fifth row, depends how you index. In this case, the shape is one row, 50 columns, no, because it was a 50 by 50 matrix. If you collect a single element, you can say the row, in this case, it's the element row 2, column 3, okay? Or you can do other things, like, for example, getting some consecutive rows or columns, okay? Or a set of non-consecutive rows or a set of non-consecutive columns. Remember that unless you do the collect, these data are as future objects. It's a new DS array, but you're not accessing here the data itself. It's just the reference. Or in this case, in the last example here is a set of 5 rows and 5 columns, for example. Okay, so you can see in the shape, it's 5 by 5. Okay, now, and the original shape was 50 by 50. Okay, we created the array here. Well, I didn't create, but was of 50 by 50. Okay, but here, since I'm just accessing 5 by 5, the shape on this case is 5 by 5. Okay. You have some functions, for example, like the one I mentioned before, to compute the mean. In this case, along x is 0. Okay, or the transpose of the whole matrix. Okay. Since if you don't add the collect, you will not have the data, as I said before. Okay, so these are examples of how you can create and manipulate data or access data in slices and so on. We will go now into a first example of usage of one estimator. Okay, we will do an example with k-means. Okay, in this case, the data we will create is using this make blobs, which is a scikit-learn function, which creates data in, well, a blob is a kind of a cloud of points. Okay, in this case, you will see if I print it. Okay, I get both in this case, it gets both the data and the labels, although for the clustering, we're using the samples. Okay. If you print it here, you will see that it have created these 3 different clouds. Okay, and that visually, as I said before, it's very easy to create a cluster. No? But if we are not able to visualize, it's not that clear. No. So this data, the x and p that we got as result of calling them make blobs, this is a NumPy array, but you cannot pass a NumPy array directly to a Dislib function. So you can convert it. In this case, we converted using the DS array invocation, but passing as parameter the name of the array x and p, okay, and the block size. The original data is of 1,500 and it's of 2 dimensions. Okay, these blocks are of 2 dimensions. So we are doing now 5 blocks of 300 by 2. Okay. Okay, so with this, we can then instantiate, for example, the k-means estimator. So this will create the reference object, km, for calling, for example, the fit and predict. Okay? And we are creating with, just as an example here, with two clusters. No? Probably you will say, no, this doesn't make a lot of sense because we can clearly see here that there are three centers. No? But I want to show this a bit graphically. Okay? So we do the instantiation, and then you can call the fit. Okay? You can also print the centers, and then you can use the model, KM now, to predict, and using again the same data. So we are using the input data for getting the labels that the model has created. Okay? So now we have in white red the labels that have been predicted by the model. And we can plot this. Now this will be plotted with different colors. Okay? So the purple, it's one cluster, and the yellow is another cluster. No? And you can see here that, well, this clustering is not very smart, no? Because these two groups are not very good. So you can go back to the notebook, and now instead of defining two clusters, you can say three, and you can rerun it. Okay, so the notebook enables you to rerun it again. You do the fit again, and you can print the centers again. You'll see now that we have three centers, and predict again. And if I plot it again, now it looks a bit better. No, we can see here now the three clusters. No, so you can do this. Would be like the iterative thing. No, imagine we say 4. You can do it again and again. It will not be very good, no, because with 4 again, the prediction is not very good. No, again, it splits this. For some reason, decides to split this one. Probably there has some. I don't know why it decides this one. Probably this with 4. Probably there are different possible solutions. The one that looks better is with 3. I will print it. I will do it again with 3, so we have a nicer. Okay, so the algorithm is very similar to the k-means that Javi was showing in the morning. Okay, just that in this case is with the TS array structure and inside the code. If anybody is interested, you can go into the code and look into how this has been parallelized internally. Now, if you stop it, I prefer to stop it because the task graph will be a bit large. Okay, well, if I, okay, now, if I go to the monitor, internally, this is a PyComs application. Okay, so this has been running different multiple tasks. Okay, at the beginning, we have some tasks for creation with random, others with reading from files. You see here filter columns. You have many different functions. No? And at the end, you see the k-means ones. These are the tasks that we have in the k-means. Okay. And you have then the statistics, no? The number of tasks that have been run, a bit of the estimated time, the measured time that it takes to run, and so on. And if you look at the task graph, if you look into the complete task graph, okay, if you unzoom, for me it works like, well, yes, just typing here and trying to unzoom. Okay, you can see the whole, well, the first tasks that are between them, all of them parallel, are the first that we run for creation of arrays, slicing, and so on. And then we did other operations, and here those that has a similar pattern, these small trees, these are the k-means. In this case, are quite small. Remember which data structure I created? We had 1,500 points, and we did blocks of 300. No, we had 5 blocks. No, and you see here, no, that you have 5 tasks here in parallel. So this gives you an idea, no, of how the parallelism is created. We have one of these tasks per each of the blocks, no, and since the k-means have iterations, so the red thing is a synchronization point where we get the new centers and compute again, okay, and so on. And then here is when we did the new k-means, okay, because here this kind of another green tasks probably is when we were collecting the centers, okay. K-means base, I cannot see the whole name here. Base predict. No, when we did the prediction, sorry. Okay, yeah, this one is the predict. Yes, I was wrong. So in this case, we were using the initial model before plotting. We do the predict, no? And you see again, no, we have for each of the blocks one task that does the predict, no? So it has a very similar structure. Okay, so basically this is how it works internally. Okay, the Dislib. Okay, then we can go now into another notebook. You have two notebooks that are called 11 dot something. We will start with the 11.0 exercise blanks. Okay, it means that it has some. Well, in this case, I run it. It has some of the boxes that are not complete, and I will allow you to fill them. Okay. So we begin at the same starting box, no, that we start the runtime, and then we start the Dislib. Okay. And again, we will use first the data set of the blocks, okay, the ones that we were using before. So let me know if you can run it up to here. If not, maybe, I don't know if any of you need some help to run up here. If you are able to run the notebook. Okay, no complaints. Vale, perfect. So now instead of doing the clustering with the k-means, what I will well, I will allow you to do it yourself, but with the DBScan, I will not allow you a lot of time here because it's not very difficult, but at the same time, it's the first one. No? So the first one, I will help you a bit more, and the others, I will allow you more time. In any case, no, to instantiate the DBScan, in this case, for example, it has two parameters. No? K-means had the number of clusters. The DBScan has the epsilon and the mean samples. These are two parameters that use internally to the clustering algorithm. You can go into the link here you have of the API. It goes directly to the DBScan page. Let me enlarge it a bit so you can read it better. Bueno, so the epsilon by default is 0.5. So if you don't say anything, it will use it 0.5. And the number of samples, if you don't say anything, also it will use 5. If you want, you can use these parameters if you want, the default ones, 0.5 and 5. Then we have to call the predict, no? And for this, we need to pass X. No? Let's see how this is done for DBScan. No? If we look at the function, no? It's saying us to use the fit, not the fit predict. Okay. So you need to pass just the parameter, the ESR X, and the Y. In case you were passing it, it will be ignored. So we don't need to pass it. Okay? So you can just call it. No, sorry, not the fit predict. Sorry, excuse me. The notebook says to call the fit predict. No? Let me close this. So the comment here says to call the fit predict. Eh? So you call the fit predict, passing the DS array X in this case. No? So it will be dbScan, no, instantiated class with the fit predict. Okay, now. And then we try to plot the result. Well, what do you think about this prediction here? It's in fact it's creating 4 clusters, because it's like it's doing the yellow cluster, the blue cluster, the green cluster, and the purple. No, those that are like outliers. In fact, it's not classifying them in any of these. No? So it's like finding 4 clusters. You can try to play a bit then with here with the parameters. For example, here I have that before I had run it with epsilon1 and 15 samples. It seems a bit better with a larger epsilon. Okay, maybe if we do it even larger, what would happen? Oh, this is worse, because if I use the epsilon2, now it classifies all the samples in the same cluster. No, it's using a single color. So let's go back to the one. Okay, so you see here, no, that this is one of the problems. No, what parameters to use, no, for these estimators. Okay. Let's now try with a different data set. Okay, instead of the blocks, we will use the circles, which it does a kind of a concentric. Instead of having a single cloud, it's like 2 circles of points. You will see when we print it. Okay, and it's another data set where k-means will not be doing as well as before. Okay, we will compare k-means and dbScan for this other data set. Okay. So now in this box, the idea is that you create the DS array from this XMP. Yes, so you create the DS array, and then create estimator for k-means and for dbScan, and call the fit predict for k-means and dbScan. Okay, we have done everything before, so you should be able to do it yourself. I allow you 5 minutes, okay, to solve this box. Okay. Now the only hint is for k-means use 2 clusters. Okay. Well, we can change this later, but use 2 clusters. Okay, I will start slowly. So okay. So first is the creation of the DS array. We have done it before in the other notebook, for example. We can do it the same way. So if you look at the previous notebook, and we did the k-means. For example, I did here this DS array, XMP, and block size 300 by 2. No? So you can do the same. Or as you saw, since the block size has impact on the way the parallelism is dealt, you can decide to do another block size. No? Or imagine you say, well, I would prefer more parallelism. Well, let's say that we do 150. No? We have 2 more double number of tasks now, for example. No? It's an alternative. But be careful not to do it very small, so you don't have a very large number of tasks. Okay, then next, besides importing this case k-means, we have to instantiate the estimator, no? The k-means, and I told you to use 2 clusters, for example. Okay, and the same for the dbScan. For the dbScan, the parameters, you know, we have done it before. No, the epsilon, we can use or the default or the same that I was using above, I was using 15, no? Here, the default is 5, I think, no? I said. And then you can call the fit predict for the two methods. And for the k-means. And you can run it. Now I'm running the two algorithms at a time, okay? And if I plot the results, well, now it didn't went too very well for the DB scan, but neither for the k-means. I think that when I was using 5 samples here, it was going better. You can rerun it. No. Epsilon. Sorry, I was using 0.1, not. Okay. Try with a smaller epsilon. Okay, now. So you see the scan here is very sensible to the epsilon, no? Because when I was using 1, it was giving like a single cluster, but with 0.1 is able to differentiate the two rings, no? But the k-means, if you try to change the clusters, well, it's clearly here there are two clusters, no? The ring outside and the ring inside. But whatever you do, in this case, this algorithm is not able to detect this type of data sets. Okay? So this is inherent to the algorithm, no? The way it classifies the points given the position, tries to find the center, okay? And here it's impossible that detects that this is one cluster and this another. But however, the DB scan, it's able to detect this, okay? So even we have to play with the parameters, the way that DB scan classifies the points, it's able to cluster this in a better way. Okay? So we will speak later on how to find the parameters, okay, with the grid search. Okay, let's now play a bit with the classification example. Okay, we will play now with the digits datasets, which is also in scikit-learn. Okay, these samples represent images of handwritten digits from 0 to 9. Okay, so in each of the digits, what we have is multiple pixels of this image. Okay? Each of them has 64 pixels. Okay. So if we look here, for example, the digit that is the data that is in the 23, well, the numbers doesn't say a lot to us. But if we plot it, okay, with this, we can see, well, you can intuit, you can guess that is a 3, okay? And if you look at the label, you will see that the label is 3, okay? So in the labels, we have the number, the handwritten digit, okay? And in the samples, what we have is the pixels in a 64 by 64, sorry, in a 8 by 8 matrix. Okay, so these pixels are these colors here represent what is the value of each of these pixels. Okay, the values here represent the value of the pixel. To make this classification a bit easier, we will not work with all the digits, but we will the labels we will make the module. Okay, so we'll only look if it's an even or odd. Okay, so we generate a new set of labels, and it will be 0 if it's even and 1 if it's odd. No? So now for Y23, which had the 3, the label is now 1. Okay. Okay. So we will need now to use this data to classify the digits into even and odd. Okay. Okay, so the first thing is that we split the data set. X and P were the samples and Y were the labels. Okay, so we split it into sub data sets. The training data, so we'll have both the samples and the labels for the train, okay, and the samples and the label for the test. This is splitting into 75 and 25%. Okay, so this function is also from scikit-learn still. Eh? So now we have 4 NumPy arrays. X-train, bueno, sí, son arrays. The X and Y train and the X and Y test. Okay? Well, this first, what it's doing is reshaping the data. I will not go into the details why the reshaping is needed. But then from all these data sets, we need to create the DS arrays. And you have here the creation of the train data or conversion of the train data into DS arrays. And we are asking you to do the data arrays for the test data. Well, this is relatively simple, no? You want to do it now in 1 minute, and then I'll put the solution. But what is more tricky here is the size of the block size. Okay, so you need to create a DS array for the X test. And the block size, in case you don't know which one to use, the best is to use another example that you have. In this case, that's 300 by 64. In fact, if we are using the same type of data, what would be logic is to use sorry, there is a question about the CSVM, but I'm still not there, so I will continue with the example for the moment. Okay, I will answer the question later. Okay, so you can convert the data in this way. Yes. I don't know if you did in a different way. And the next thing that we ask you is to instantiate and train the Cascade SVM estimator. Okay. So in the first row, what we ask you is to instantiate, and in the second, to fit with the training data. Okay. And you can use the API that is here. Okay. So if you go to the CSVM, you can see an example which you can use in a similar way. Okay. For the last part of the box that gets the score, gets the accuracy, wait a second, okay? I will do it for you. Okay, so we can instantiate the CSVM. This has a parameter, okay, gamma. I will use now 0.1, okay, or the default. We can use the default one. Let's see what is the default. Ah, okay, no. Well, let's use 0.1 for the moment. Okay? If not, has a default value. And we can fit CSVM, fit We use the train data, okay? Okay, then to get the accuracy, if you look into the API, you see that we have this score function, okay? So given the parameters, the test parameters, for example, it will give us the accuracy, the mean accuracy that is obtained with this model, okay? The problem with this is that it's a future object. So if you try to just to score equal CSVM dot score, and then you pass the test arrays, okay, as parameters, and you're trying to print the score. Just do it this way for 1 second. I was expecting to get an error. Okay, okay. I wanted to get this, and I don't know why here I didn't get this error. So the problem here is that the CSVM score returns a future object, okay? And if we want to look at the value, we need to use the PyComs wait on, or the coms wait on, the same way we were using it before in the demos or the hands-on that we are doing with Javi. No? So now if you run it again, well, if you don't want to run it again, add another box here because coms wait on not defined, sorry, should be coms wait on. I will put it in another box so I don't have to run it again. I will run everything again later. Vale, now, vale. You see, it's a very slow accuracy. Okay. I don't know, Pedro, was this your question about the accuracy, or because you say that with Cascade SVM, the result is deterministic, and with random forest is not? But I have not done the random forest example. Well, yes, if you change the gamma, you will get different values for the accuracy, and we will play a bit later. Bueno, sorry, here again. Well, now I have an overflow. No sé, I don't know why I get this overflow now. Let me stop or maybe it's a very big value. This. Okay, I guess the gamma cannot be that big value. Okay, that's why I was getting the overflow. If I use a smaller gamma, I should get a better value. Okay. Okay, yes, but this is part of what I wanted to show in the last example. Okay. Okay, now we see here, no, again, that the parameters is not something that we can guess easily. Okay. If you use in this case, with a larger parameter, we were getting a very bad accuracy. Okay. Let me close this. I don't need this one here. I don't need this one here. So now in this box, the idea is that you try to do the classification, but now with a random forest, similarly to what we have here for the CSVM, but with a random forest. Okay. I leave you. Yeah, because the collect is a function that is from the class, and in this case the score is not a DS array. The collect is to collect. see, and it's not working for the score, and this is something we need to work because it's also not very nice that we have to do the comms weight on. I would prefer that the score can be the comms weight on inside the Dislib, so we don't have to call to comms weight on. It's not very clean, no. But the collect is only for the DS arrays. In this case, the score is a single value, and we cannot use the collect. If you try it, you will see that it fails. Yeah. No, what you would expect is this, to use the collect, but it's not. So for the random forest, you have the similar thing, ¿vale? You create the estimator, you call the fit, and also you can print the score. For the random forest, if you check the documentation, you see that there is a similar similar function. Okay. Okay. So we can do. Well, first we need to import the class. Okay. Then we can instantiate the random forest classifier. You can call the fit. It's very similar to before. Okay. With default values. And you can well, you can do it in one line or in two, whatever you prefer. You don't need to import again the comp weight on. If you want, you can do it just as in a single line, but if it's with two, it's the same. Okay. So this is just a matter of paste. Okay, this is the same that we had before in 2 lines. No, before we were getting the score and then waiting for it and printing. Here I put it in a single line, but it's the same. Okay. There is an error. Okay, so this is the nice thing of the notebooks that you can correct and play again. Yes, a ref score exists. It doesn't work for you? Ref dot score. Did you import the class, the random forest classifier? So I don't understand. Can you look? It's working for me. Can you look what is the difference? So I don't have to go. So I don't know why. So Raf, did you use any parameter to get the .96? Okay. In random forest? Okay. Well, it works now or no? I don't understand what is the problem. No. But did you import the computer before? Maybe it's complaining for the computer. I understand. Maybe that. Well, yeah, well, score. choose not a score. Okay. You need to use the same identifier. No, it's okay. Okay, so you see here that in this case we can get very different values, of the estimators and of the score. In this case, the accuracy. So that's why we can use the hyperparameter optimization. The hyperparameter optimization, what enables us is to evaluate, for example, for a given set of parameters. Here with the CSVM, we were using .1, I was using gamma.1, and there is also another parameter C that you can also, if you look into the description, CSVM, you can also pass the parameter C. By default is 1, okay, but you can give another value. So if you want better accuracy, maybe you need to set it to a different value that is not a default. So in this case, what we will show is how we use this grid search. Okay, I will do the example for you. Not very difficult, but just that maybe if you have not done it anytime, I will guide you through the API, but I will do it for you. So we will use these parameters, these three combinations, against these three combinations to see which one is better. So in this case, we will use the grid search. If we go into the API, and you look for the classification, the model selection, this grid search. So you pass it an estimator. In this case, the estimator will be the CSVM and a set of parameters. And what it's going to do is to run the different models with part of the data, okay, and decide which of these parameters is better. And then you can use it later to train again with the better parameters. So here we do the instantiation of the grid search, okay, grid search CV, and you use the CSVM as parameter, okay, and this structure, the params, these params, which is a dictionary, okay, with these values for gamma and for C, okay. So you create this first, and then you can call the searcher directly, okay, .fit with the train data. The same data that we were using before takes the S train and the Y PS train, and you run it, okay. This, well, if you use the correct values, PSVM, okay. This takes a while, okay. So while it's running, we can go back to the monitor if you want to see if we see anything running there. Okay? Since it's very long, so I can refresh and go into the second, and maybe here we will touch. Okay, so you see here, what the monitor, since we are running with a Docker image, it's very difficult to see at the same time the tasks that are being executed on the graph. Okay, but with this larger example, we see a bit more. You were able to see part of the graph, that was under execution. Here another part, because it's executing a very large number of tasks. In fact, if you go here into task information, you can see a summary of the number of tasks. You see here 370. This was the DB scan, but even the ones in the bottom should be even more. CSVM. Well, I show now for 462, 500. So you see, it's running quite a large number of tasks, even it's a small example. Okay. So internally, this is decomposed into invocations to the CSVM. These are CSVM tasks. If you look the color, is the same train task that we were looking in the code. that builds this type of inverted tree. Okay, so this will be running for a while with the objective of telling us which of this set of parameters, the values for gamma and the values for C, will get us a better accuracy. Okay. Still running. We can also check the different functions of the grid search. You can see that there is a single function for fitting. No, the fit. Sorry, it went to it. I didn't want to go here. I went to the wrong position of the. I don't find now the grid search. Okay, let me go from the notebook. Here. So we have the fit. And then you can also get some parameters of the result. Okay, you will see that we can look into the results. Okay, and check the parameters. Okay? Well, this has finished now, and okay, now it has finished, and in this in the search of CV results, okay, we can use this data frame to print the result. Okay, so basically what is showing here is this is a dictionary with the different options, no? With C1, gamma 0, 1, C1, 0, 0, 1, and so on. The different combinations of these parameters here, and the accuracy that is obtained, 49, 92, and you see that the larger, okay, is here with C100 and gamma .0001. Okay, for these values is the values for which this CSVM will run better. So we can use these values here. Okay, and rerun the CSVM again, and you will see. Now with the whole data. Before was doing like chunks of the data, not using the whole data. So you see the way to improve the models, okay, a bit will be this iterative thing. No? You can run with the grid search or the random search or other searchers with some parameters, okay, and get the best combination to finally train the model. Okay? And now this 1.99, 98, for example, is larger than before the random forest. Okay, although with a random forest, we can do also similar. There are some parameters also of the random forest that we can also play with and try to look which will be the optimal. Okay. Okay, and then you can close. And if you want, we go back to the monitor, whatever it is. Okay. And we can check the final task graph. So this is still, this will be a bit big, so maybe it takes a bit of time to generate it. This one was generated. We could see this one. This was from the first notebook, okay? Now I'm trying to get the other one. This was the first demo. And here. Well, It's processing it. Okay. Well, while I'm trying to gather the task graph, I don't know if there is any question. Okay. So this was the final exercise for the Dislib. I will then show the agenda for tomorrow. In the meanwhile, trying to see if this is able to visualize the task graph. Okay. So tomorrow we start at the same time, okay? 9:30. At the beginning, we have a session on Java. Okay, so I shouldn't have done this. Okay. Okay. So the first session will be on Java, on applications with Java and C++. Okay. And we will do also hands-on in Java. Okay. And then there will be another session on some other features of comps. Okay. Also, here in this second session, there will be some demos, some additional notebooks that you have. You can also run it or just allow me to show it to you. Okay. And then also some slides about the comps execution environment, the lunch break, and then we have hands-on in Mare Nostrum with some examples a bit more advanced. And at the end, a summary of how to install and final notes of the tutorial. Okay. Okay, so if there are no more comments, let's see if I was able to get the task graph. Taking into account that this is running in my Docker inside my machine, so sometimes it takes a while to get the task graph. Okay, the task graph is more for demonstration, and it's not something that you need to use all the time. Okay, so now it seems that I don't want to finalize. Okay. Okay, so if there are no other questions, we will stop here.